Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture 5, and we are in part 7 of chapter 2. And so we have been talking about hypothesis test with the two-sample case. So we're going to continue, and we're going to actually conclude this portion, the hypothesis test portion, in this video. So as has been mentioned, we have to check assumptions in order to know if our analysis is any good. And the assumptions that we have for the two-sample test, whether we know the variances or don't know the variances, whether the sample sizes are small or the sample sizes are large, the assumption is that each of the samples has a normal distribution. So we have to check the normality of each sample. And when we have small sample sizes, a histogram is not going to give us a good picture because we don't have enough data points to form a good histogram. And changing the number of bars on the histogram will greatly alter the shape. So we needed a better tool to do that, and we have one. It's called the normal probability plot, or the Q plot. Sometimes we use capital Q, sometimes we use little q, sometimes we just say QQ plot. So there's a lot of different ways that this is set. So this is figure 2.11 out of the textbook, and it shows the strength here, and it shows the normal CDF value up here. The percent of that, actually. So the normal CDF as a percentage. So they've multiplied by 100. And what we're looking at is there's a line for each of these samples. So this is the modified sample with the latex polymer emulsion in it. And the squares are the original formulation. And in both cases, we see that the points are fairly close to the line. Now, the scale that you use is also important in how close or how far they look. So if you cut the graph here and zoom in, then the distances away from the line will seem larger. So that's something for you to note. So what they've done is they've gone from practically 0 to practically 100 here. So they've gone through the whole range. They didn't cut this off at, say, 5 and at 90. Okay, so that's something to keep in mind. And what we're looking for is we're looking for large deviations from the line. And we don't really see that in either graph. Now, we're more concerned about points that are far away from the line in the middle of the graph, rather than over at the what we call the tail of the graph. If we have a point that's, let's say, that's over here, then we're not so worried about this point here as we would be that point if it were, say, here. That would be an issue, that far away from the line in the middle. You see, when we're in the tails of the distribution, when we're up here above 95, we are, so I probably should move the point up higher so that it'd be more realistic. When we're way up here, we're in the percentages where it's very unlikely that you're going to get a point when you have a small sample, because the probability of getting a point is so small that having a point there is unlikely. So with that, we know that any point that we get that's that extreme maybe not it's maybe not so unusual that when we do get a point that it doesn't fall near the line. So near the tails, we are not as concerned. It's in the center of the graph that we want to be concerned about. Okay. So these look very nice. Now, we ran this using R. So here is the code, and I have put a a category called code at the top of the Moodle page, and I have put a data file in there with all of this code. And it says for students, and so this is the file that you should be using for homework and for your project that is coming up. Okay, so I've run this code here, except my data, this is my data name, so I could name it anything. And in that file, I don't have Portland, I have like Y0, but this is just an example of the code. And what I need to point out to you is that the strength, this is a flipped screen from what we have up here. This was made using a different software. So they have strength in the X and the normal plots on the, or the normal quantiles on the Y-axis. We have it reversed in R. The strength is on the Y and the normal quantiles are on the X. But what's really nice about this function is that it puts the 95% confidence intervals in there. So we can see that we have a point. If I saw this point by myself without the 95% confidence interval line here, I would wonder if that was a significant deviation away from the line because it's near the middle of the distribution. But having the 95% confidence interval or band around here shows me that all of the points, well, I didn't include that one, did I? So all of the points, well, fall within that confidence interval. So, and the same is true for the other distribution. This is the unmodified. And so all of the points are within the confidence band, so we can be comfortable saying that they're both from normally distributed populations. Okay. So we've checked the assumption of normality. Again, the two-sample t-test is robust for small to medium departures from normality. So, so if we have one outlier, it may be okay. The problem is that we need to make sure that we have equal variances or not. And some of these tests are sensitive to departures from normality. So if we have an outlier here on our QQ plot, then we have to be very careful because the test that we choose has to be one that's somewhat more robust. So if we have outliers, we would not use Bartlett's because it's sensitive to departures from normality. So what we're doing here is we have our own hypothesis test, and that is that sigma 1 squared is equal to sigma 2 squared, or you can do it for sigma 1 equals sigma 2. Either way is okay. Because these are positive quantities, squaring gives the same relationship. If they could be negative, then we'd have to worry about this, but we don't. So against the alternative that they're not the same. Now, this is one of those cases where we're backwards. We are operating backwards from what we would want to do in a test. The test can really only show the alternative. And what we want to know is, are they equal or not? So we have to be careful. If we set alpha equal to 0.05, which is normal, and we reject, then obviously they're different. But what if we don't reject? What if alpha is equal to, or what if the p-value is equal to 0.10? Do you still feel comfortable saying that they're not, or that they are equal, when the chance of, when the probability of us getting such an extreme difference in the standard deviations or variances is only 10% if they are equal? See, so we have to be careful with how we think about these tests. Okay, so here is the code for Bartlett. And this is stack data, meaning that we have all of the data in, say, strength is all in one variable, and then we would have treatment as another variable. So we'd have the unmod, the mod, all, so everything's in, all the strength is in one column, so that we would call stack data. And what we get is we get the k-squared, that's the test statistic, of 0.50292. The degrees of freedom are 1, and here is the important thing, that the p-value is 0.478. So we certainly would not say that they're different, okay, at that. However, this is less than 0.5. So I'm pretty comfortable saying that they're the same with this, but I would still be very cautious. I would like to run them with both the assumption of equal and the assumption of not equal, and make sure that I get the same result in this case. So that's a personal preference there. And here is the code if it's unstacked. In other words, if we have modified in one column and unmodified in another column, the strength variables. This is how you would do that. And of course, you get the exact same results either way, so that's good. So what's our decision here is we failed to reject the null hypothesis, okay? That's our decision. The conclusion there does not exist sufficient evidence to support the claim that the variances in the modified formulation and the unmodified formulation are unequal at a 95% confidence level. The test was performed using a sample of N1 equals N2 equals 10. That sample size is important to know how powerful our test is. And with such a small sample size, the power is not very good there. Now, the second test, if we had had outliers, this is the test that we would want to use because it's less sensitive to departures from normality, okay? And so it's called Levine's test, and here is the code. This is with the stacked data. I imagine you can do it with the unstacked data, but I didn't look that up. So that would be something to look in the help function for. And I imagine that you can. It's just a matter of specifying the right variables there. So Levine's test, it gives us an F value right here, and then it gives us a P value here. Oh, and here are our degrees of freedom, 1 and 18. Because it's an F test, it has 1 degree of freedom in the numerator, 18 in the denominator. Our P value is 0.1793. That's getting a little small. So that starts to concern me that maybe they are different. And we have they're close, but they are different. So that could affect us. But let's look at another test. And this is the F test. And it is very, very sensitive to departures from normality. You do not want to use this if there is an outlier ever. So here is the code for this one. And let's look at the p-value here, 0.4785. We have an F test, and we've split up 9 degrees of freedom in the numerator, 9 degrees of freedom in the denominator. What we have here is we have sigma 1 squared over n 1 minus 1 over sigma 2 squared over n2 minus 1. And so this is a chi-squared, this is F, I'm sorry, it's an F. These are both chi-squared. This is a chi-squared n1 minus 1 over, divided by n1 minus 1, over a chi-squared divided by n2 minus 1. And so that is an F distribution with n1 minus 1 comma n2 minus 1 degrees of freedom. So that's one of the transformations you need to know. So when you see this degrees of freedom broken up like this, and they have equal degrees of freedom or equal sample sizes in the two samples, that tells you how they formed this test statistic, that they did it like this. Okay? So we have our test statistic value, we have our degrees of freedom here, and that's getting messy. So in this line, we have our data in that line right there. Okay. They also give us a 95% confidence interval for the difference. You'll see that 0 is not included. If 0 is included, then our p-value would be, let's see, so the 0 is not included. That's interesting because actually, yeah, So, but we never get 0 for an f-test. I'm sorry. What we're looking at here is if 1 is in there. 1 is in the interval. Because when we take a ratio of chi-squared statistics, if sigma 1 squared is equal to sigma 2 squared, then when we do this division, and I'm saying sigma here, it should be S. So what they do is we don't know sigma, so we take S1 squared over S2 squared, and we divide each of those by their degrees of freedom, and this is an F statistic, okay? So if these are the same, we expect this to be this ratio to be close to 1. And so we see that 1 is in the interval, so we cannot reject the null hypothesis here, okay? So the importance of the t-test, the two-sample t-test, it's an objective framework for these simple comparative experiments. You can think of these as a one-way analysis of variance or factorial design. And so if you remember back to, with the 2 levels, one way with 2 levels, all of these hypotheses involve the mean response at one side of the cube versus the mean response at the opposite side of the cube. If you remember, we drew, and I can't draw a cube very well, but we drew a cube and we said that that we had we might have one parameter here and we might have another parameter here that we're checking against, that we're testing against. Okay, 2 different levels there. So if we have equal variances, and I don't know why this showed up here the way it did. I guess I had my cursor there, I'm sorry. This is the code to run the t-test, the two-sample t-test. Here is the first sample. Here is the second sample. The alternative is 2-sided. We can have one dot side, or I'm sorry, not one side. We can have less than or greater than. Less, greater. So always look in the help for this function, the t-test, and you'll see what your options are to fill in here. And var.equal is true because we said that we did not fail the tests for equality of variance. We could set them equal to true, and so we've run it here. And what we see is here are our results. We have the test statistic, which is a t-value, negative 2.1919, degrees of freedom 18. Why is this value different? We got like a negative 2.207 or something. It's because of rounding. The values we used in the example were provided to 3 decimal places by the authors, and the rounding has made that big of a difference. And the p-value is less than 0.05. So the p-value is less than alpha, 0.05. So 0.04177 is less than 0.05. So we reject the null hypothesis that the means are the same, and we say that the means are different. And if we look at the confidence interval here, it does not contain 0. And that tells us that mu1 is smaller than mu2, and that's how we calculated it. X bar or y bar 1 minus y bar 2. Now, if we run the same test and we just change this to false for equal variances, this is the test statistic that we obtained. It's a little bit different, and we get a degrees of freedom 17.05, and remember, we had 17 degrees of freedom when we did the calculation. I just rounded to 17 because our table only has whole numbers in it. And the p-value 0.04, and again, that's less than 0.05, so we would, again, reject the null hypothesis. So in both cases, whether we assume equal variances or not, we're going to reject the null hypothesis that the means are the same. And so in both cases, when we see that we get the same result for both cases, then we know that regardless of our assumption of equality of variances or not, there is a significant difference between these two means. All right. So that's it for the confidence interval, or for the two-sample t-test. I hope this little video has helped bring that together. And again, I've provided you a file that you can use for your homework, and I've provided all the code in there, and I've actually done an example, this example, and walk through how you would do it for a homework situation. If you have questions, come to virtual office hours. If you need help before then, email me. I'll get back to you as soon as I can, as soon as possible. Please take care of yourself, so we will see you next time.